Simple harmonic motion, 4th hour questions, 2 through 5. Question 1 and the multiple choice questions were answered in a prior video. Question 2. A 0.25 kilogram ball is dropped from a height of 10 centimeters onto a spring. If the spring has a spring constant of 60 newtons per meter, what is the distance the spring will be compressed, or what is the amplitude? We're going to neglect any energy loss in anything other than spring compression. And then, on recoiling upward, how high will the ball go? So for the first part, we're going to say at the compression point, once the spring's fully compressed, that the gravitational potential energy at that point goes to 0. So all the spring potential energy, the compression energy, is going to come from the dropping of the mass onto that spring. So we are going to say that the maximum potential spring energy is equal to the maximum gravitational potential energy. So we're saying these two things equal to each other. Spring compression is 1/2 the spring constant times the amplitude squared. Gravitational potential energy is equal to the mass times gravity times height. Now we're going to have an unknown in terms of the compression. So there's going to be an a on both sides of the equation. 1/2 60 times a squared is going to be equal to 0.25 times 9.8. And again, we're going to use 9.8 on homework problems, but you'd use 10 on the AP exam, times 0.1, the dropping height, plus a, which is going to be the compression of the spring. We're going to solve for a using the quadratic equation. So subtract everything to the right-hand side. So we're going to get 30a squared minus, when we solve for and resolve for the formula, 2.45a minus 0.245 equals 0. Use the quadratic formula. We're going to get two answers here. We're going to take the positive answer is it's going to be compressed 14 centimeters or 0.14 meters. Part B. Since it was dropped from a height of 10 centimeters and it's compressed, then that compression energy, due to conservation of energy, has to then return the ball to the same height. So it goes from gravitational potential energy into spring compression energy plus the velocity till the compression energy is maximized. Then, once it's maximized, it's going to then return the energy back into the mass. And then it's going to come back to total gravitational potential energy. So it has to return to its original height of 10 centimeters. Question 3. A mass in a spring oscillates vertically with an amplitude of 15 centimeters and a frequency of 0.2 hertz. The equation for this motion, because we're going to be starting at y equals 0, we're going to use the sine function. So the height at any given time is equal to the amplitude times sine omega t. And we're going to say the initial motion is upwards. What's the position and direction of the motion of the mass in 3.1 seconds? So y is a function of t, and y is equal to a, the amplitude, times sine omega t. Omega can be broken down into more basic parts. Y is equal to a sine 2 times pi times frequency, which is omega, times time. We're going to substitute in our information now. Y is equal to 0.15 sine 2 times pi times the frequency 0.2 times 1.3 seconds. Solve for this and make sure you're in degree mode, not radian mode, and you're going to get y is going to be equal to negative 0.1 meters or 10 centimeters down from the equilibrium position. Part B is asking how many cycles will happen in 12 seconds. We can't find this out directly, but we can find it out indirectly. We're given that the frequency is equal to 0.2 hertz. The frequency is the inverse of the period. The period is how many cycles happen per unit of time. So when we take the inverse of the frequency, we find that the period is equal to 5 seconds. So it takes 5 seconds for every cycle to occur. In 12 seconds, 2.4 cycles occur. Question 4. A block with a mass of 0.25 kilograms is sitting on a frictionless surface and is connected to a spring that has a spring constant of 180 newtons per meter. If the block is displaced 15 centimeters from its equilibrium position and released, what are the total energy of the system and the speed of the block when it is 10 centimeters from the equilibrium position? With what we're given in the equation, we can find the total energy of the system very quickly, and that's equal to 1/2 times the spring constant times the amplitude squared. So 1/2 times 180 times 0.15, again, make sure you're changing that into meters, squared. And so we get 2 joules. Also, with the given information, we can then solve using our velocity equation that the velocity is equal to the square root of k divided by m times the amplitude squared minus x squared. Substituting in for our equation, we find that it is the velocity at 10 centimeters or 0.1 meters is equal to 3 meters per second. Last question. This is trying to tie together a lot of different things from both circular motion and gravitational motion and a simple harmonic motion. An asteroid has a pendulum on it, and the length of the pendulum is 85 centimeters. The frequency is 0.07 hertz. What is the acceleration of gravity on this planet? And if the diameter of the spherical asteroid is 1.5 kilometers, what's the mass of the asteroid? Our fundamental equation is that the period is equal to 2 pi times the square root of L over G. We also know that the period is equal to 1 over the frequency. So by resetting our equation and solving for G, we get that L times 4 pi squared times the frequency squared is equal to the acceleration of gravity. Plugging in what we have for our values, again, making sure that we're changing things into meters, we get 0.85 times 4 times pi squared times 0.07. So we get an acceleration of gravity on this surface of the asteroid of 0.164 meters per second squared. Whenever we can write a force is equal to, then this connects all of our problems. We can say that the force of gravity is equal to mass times gravity. We can also, using Newton's universal gravitation, say that force of gravity is equal to Cavendish's constant times the mass of the planet divided by the radius of the planet squared. You can see that the little m's are going to cancel out on both sides, and so that we're going to get G is equal to big G times m times the radius squared. We're not given the radius directly, we're given the diameter. So using the definition of diameter, we're going to then solve for solve for m. Little m's are going to cancel out, and we're going to get our final equation when we plug in and solve that the mass of the asteroid is 1.38 times 10 to the 5th kilograms.